Hello everyone. Today we're diving into an advanced and powerful extension of the genetic algorithm approach to weight control, which we explored in a previous video. This presentation is a direct continuation of that original weight control exercise. You can find it higher up in this playlist. If you haven't watched it yet, we strongly encourage you to pause here and watch that video first, as today's topic builds directly on that content. Let us quickly recap where we left off. In our previous exercise, we established a clear goal: save at least 28 pounds of weight from our VTOL aircraft, which represented our constraint in the genetic algorithm. We were looking for a minimum cost solution, and that goal was guided by our fitness function. As you can read from the printout next to the graph on the left, we achieved excellent results. The 28-pound weight reduction target was reached, and at a minimum cost of $391. The algorithm recommended focusing on transparencies, power pods, electric lights, rotors, and the landing gear. However, there is a limitation. In our previous setup, if we want to check different goals for the weight savings, say 35 pounds or 20 pounds, we must rerun the algorithm each time, with a different constraint on the viable solutions. While this approach works, it's time-consuming and inefficient. But what if we could analyze all possible combinations of minimum cost as a function of weight savings, all in a single run? What if we could produce the full spectrum of possibilities and display it as a single comprehensive curve? It turns out we can. And we will accomplish this using a sophisticated variant of the standard genetic algorithm, called the Non-Dominated Sorting Genetic Algorithm II, or in short, NSGA-II. It is interesting to note that genetic algorithms were initially conceived by John Holland in 1975. It took almost 20 years for multi-objective variants of these algorithms to emerge, with the NSGA-II algorithm being introduced in the year 2000. Since then, NSGA-II has become one of the most widely used algorithms for multi-objective optimization. In a moment we will see the NSGA-II method in action. While traditional genetic algorithms optimize a single objective, NSGA-II can simultaneously optimize multiple competing objectives. In our case, it is both minimizing cost and maximizing weight savings at the same time. We start with Generation 0, showing a scattered population of solutions across the cost-weight savings space. Each red dot represents a different combination of cost and weight reduction. As we progress through the generations, something remarkable happens. A select group of solutions starts converging along a distinct curve. This curve is called the Pareto front, named after the Italian economist Vilfredo Pareto. Notice that our original 28-pound at $391 solution lies precisely on this curve, exactly as we would expect. Every point on this Pareto front represents an optimal trade-off. You cannot improve one objective without worsening the other. These solutions are termed non-dominated solutions. The remarkable achievement here is that the same genetic algorithm, just reconfigured for multi-objective optimization, now provides us with the complete spectrum of optimal possibilities in a single run. But NSGA-II's capabilities extend far beyond 2 dimensions. This algorithm works seamlessly in any dimensional space. Let me show you how this looks in 3 dimensions. To demonstrate this, we're adding a third variable, the time period required to complete each modification. Here are the lines in the code, showing our item properties, now including not just cost and weight, but also the weeks required for implementation. So now, instead of a curve, we have a 3-dimensional Pareto surface. This surface represents all optimal combinations of weight savings, cost, and time. You can examine its shape from multiple angles as it rotates. Note that we have also projected this 3D surface onto different planes, to make it easier to extract specific values. Every point on this surface represents the absolute best combination of our 3 objectives. No solution exists that's better in all 3 dimensions simultaneously, as these are truly non-dominated solutions. Now, Imagine extending this to real-world applications with many more variables. Consider, for example, aircraft control systems that must act on multiple parameters in real time. With the NSGA algorithm, we can pre-compute these multidimensional Pareto surfaces on a simulator, or what is known these days as a digital twin. We could also employ alternative analytical methods and add experimental data to boost the accuracy of our solutions. Then, all we need to do is convert the n-dimensional Pareto surface into a lookup table. Such tables take up very little memory space in a computer. And because the analysis has already been done for all combinations on the ground, the computer will act almost instantaneously, in response to any real-time combination of parameters. Now, we also have a list of all of the solutions that have made it to the end of the run. In our example, we started off with a population of 150 candidate solutions. Here we see that 43 of these have made it to the finish line, having been selected over a process that ran for 250 generations, or iterations. During these iterations, the algorithm set aside those solutions that were non-dominated, with each generation getting closer to the final Pareto surface. Now the designers of our VTOL aircraft have at their disposal a whole range of options to choose from. Starting from an investment of 2 weeks of work and $60, they will be able to save £7. They need to concentrate on hardware and miscellaneous, the pilot seat, and the inlet mesh. In case they have some more time and can afford a larger expense, they have the option of working for another week, spending some more money, but then being able to achieve an £11 weight saving. Should they choose this option, then in addition to the hardware and miscellaneous, the pilot seat, and the inlet mesh, they will also have to work on the rotor flanges and communication system. At least this is the algorithm's best recommendation, should 11 pounds of weight savings be sufficient. Our 28-pound goal from last time shows up here in 2 alternatives. One takes 16 weeks and costs $330, the other, while also saving 28 pounds, costs a little more, $410, but will require only 12 weeks of work. The list goes on. We have picked 2 additional alternatives from the list, going up in cost and time, but also a corresponding weight saving. Altogether, 43 alternatives to choose from. This is a lot. Again, all of these alternatives have one thing in common: they are the best all-around combination of time and expense for achieving a given weight saving. The same holds true for the best combination of time and weight saved for the same cost. One more combination will be the highest weight savings at the lowest expense for the same time necessary to complete the task. Again, these are all selected, non-dominated solutions that the NSGA-II algorithm has developed for us. Now let's have a brief look at how NSGA-II actually works compared to standard genetic algorithms. Here we see the flowcharts of the 2 algorithms side by side, showing exactly where the innovations are plugged in. Notice that both algorithms follow the same basic framework: initialization, evaluation, selection, crossover, mutation, and offspring creation. The core genetic operators remain unchanged. But there are 2 additional blocks in the NSGA-II algorithm's flowchart. The first addition is fast non-dominated sorting. This process locates solutions that excel in all parameters without compromising others. Instead of forcing all objectives into a single fitness score, it identifies which solutions are genuinely superior across all dimensions simultaneously. This is the heart of multi-objective optimization, finding solutions where you don't have to sacrifice one goal to achieve another. The second new block in the algorithms is calculate crowding distance, which seeks diversity to avoid clustering. This mechanism ensures we get a well-distributed set of options across the entire solution landscape. Without this mechanism, all solutions would converge to the same small region of the Pareto front, giving us limited options. Following this calculate crowding distance step, the selection, crossover and mutation operators are applied, just as in the standard algorithm. In summary, the NSGA-II algorithm, developed by Kalyan Moideb and his colleagues in year 2000, has revolutionized how we approach multi-objective problems. It shows us that the best solutions often aren't single points, but entire frontiers of possibilities. Finally, it is worth noting that in the last 25 years there have been some improvements made to NSGA-II. Its newer version, NSGA-III, features among others, improved diversity control, and is therefore preferable for highly dimensional problems. We may have NSGA-III covered in one of our future videos.